Hello everyone, welcome back to another video. Today we'll be running through some of the stoichiometry questions on the USNCO locals. So I've just piled up a few questions that are a wide variety of questions about stoichiometry on the Olympiad. So maybe this will help you, because the locals thing, you might have already done it, but it's coming very soon. So, question 1, or before I start, just remember that getting most of the questions right on stoichiometry is a really good way of passing the cutoff, because these are the easiest questions, right? So you want to ensure that you're getting almost all these right. So question number 3, in a sample consisting of 1 mole NaBr and 3 moles of Ki, what is the mass percent of iodine? So we have 1 mole of NaBr. Let me just 1 mole of NaBr, and we have 0.3 moles of Ki. And it's not given to you, but if you just look at the periodic table, add up the grams, obviously, you'll find that there will be 102.89 grams of NaBr per mole, which is also just 102.89 moles. And for each gram, or for each mole of Ki, there will be 166, around 166 grams. So that will be 49.8 grams of Ki. So now that we have this, you need to remember what the mass percent formula is. So mass percent is, so in this case iodine, it's going to be equal to that component mass divided by the total mass. And then we're going to do times 100 to get the percent. So here, we need to find the mass of iodine inside of Ki. So note that there's 0.3 moles of Ki. Since there's 0.3 moles of Ki in total, there will be 0.3 moles of K. There will also be 0.3 moles of iodine. This means that when we have 0.3 moles of Ki, we'll also have 0.3 moles of iodine. The molar mass of iodine is 126.9. And that's going to be equal to 38.07 grams of iodine. So now we have to find the total mass, which you can find just by adding these up. So once you add those up, you get 152.69 grams. And that's going to be our total. So now we can solve for this. 38.07 divided by 152.69 times 100. And that's going to give you approximately 24.9%. So that's going to be the percent mass of iodine, which is A. So, moving on to the second question. Lithium hydrogen carbonate, or that decomposes when heated to form Li2O, CO2, and H2O. How many moles of H2O are formed when 0.5 moles of LiHCO3 decomposes? So this question is pretty simple, but yeah, let's just look at this. LiHCO3 is going to decompose into Li2O, CO2, and H2O. So looking at the reaction, we can actually see that it's not balanced. We have 2 moles of Li, and then we have same number of carbon, we have the same number of oxygen too, and we have a different number of hydrogen. But this is pretty easy to balance, so we're going to have coefficient of 2 here, and we're going to end up with 2 carbons after putting that 2 there, so we're going to have to put a 2 here. So that's going to be our balanced equation. Now we can do some stoichiometry to find how much H2 is formed. So we have 0.50 moles of LiHCO3. Now we're going to multiply it by the molar ratio. So to cancel out LiHCO3, we know that for every 1 mole H2O, we have 2 moles of LiHCO3. And that's going to give us 0.25 moles of H2O, which is a really easy question. But the questions get harder as we go. So number 4. And I'm gonna, if I can, just gonna push that up there. Okay. The mineral enargite, or energite, I don't know, is 48.41% copper, 19.02% arsenic, and 32.57% sulfur by mass. What is the empirical formula of enargite, or however you say that? So when dealing with empirical formula or percent masses of whatever is a mineral, we can see that this adds up to 100. They're always going to add up to 100. So we're going to just turn that into grams. So we're going to have 48.41 grams of copper, 19.02 grams of arsenic, and 32.57 grams of sulfur. So now we just have to get to moles, and then we can just try to find the empirical formula from there. So, going to moles, the molar mass of copper, I think, is, for every 1 mole, we have 63.546 grams. For every 1 mole of arsenic, we have, 74.92 grams. And for every 1 mole of sulfur, we have 32.065 grams. Okay, so now when you put this into a calculator, we'll get 0.76 moles. Then for arsenic, we're going to get 0.25 moles. And then we're going to get 1.02 moles for sulfur. And it's pretty easy to see that once we divide by the lowest mole, which is arsenic, we can see that these are going to turn into numbers that are pretty whole, right? Or not whole numbers, but yeah, actually yes, whole numbers. So when we divide by 0.25, we'll end up with whole numbers. And you're always going to divide by the lowest mole, so you can get to a formula. So we can just eyeball this and see that this is probably 0.75 divided by 0.25. It's going to be 3. This is going to be 1. And 1 divided by 0.25 is going to be 4. So these numbers tell us the amount of atoms that are going to be in the formula. So for copper, we're going to have 3 atoms of copper. For arsenic, we're going to have 1 atom. And for sulfur, we're going to have 4 atoms. And remember, if we had, pretend that once we did this, we would get, Cu6, As2, and, sulfur 8, okay? Just pretend that we did. This would be the true formula, or the molecular formula. To get the empirical formula, we would divide all this by 2. So then we would get Cu3, As, and S4. But since we already got to a point where if we divide this entire thing by 2, we'd get decimals in our atoms. And we don't want that. This is the this most simplified formula, which is going to be the empirical formula. So just keep that in mind. So that means that C is going to be our answer. Okay, now I'm going to move to this side. So, when the chemical equation is balanced, what is the ratio of the coefficient of Ag to the coefficient of H2O? So here we see we have some stuff here. It's going to be a redox reaction because we see we're dealing with charges, and yeah, there's some oxidation going on here. So I'm just going to rewrite the question, or rewrite the formula. I'm just going to move this up. Sorry. Bruh. Okay. So, let's rewrite it. So it's going to be AgS plus NO3 minus plus H plus. It's going to form Ag plus NO and H2O. And I'm not going to write the state of matter because there's not really a point. Anyways, we see that there's going to be some oxidation happening here. And then for NO3 minus, there's going to be some reduction happening. And remember, reduction is gaining electrons, oxidation is losing electrons. And yeah, it's going to be 0. Anyways, let's write down the oxidation reaction for silver. So you have AgS is going to lose an electron, and we can put that as E minus. So that's going to be our electron that we lost. Now we have to write the reduction reaction. And remember, this is already balanced, so we don't have to do anything to it. So for the reduction reaction, we have NO3 minus. That 3 looks horrible. Becomes NO. And the nitrogens are already balanced, which is really helpful. However, the oxygen is not balanced. So first we're going to have to balance it. And to do that, we can add a H2O. This H2O gives us an oxygen atom, so we can add a coefficient of 2 to balance the oxygen. But note that by adding in a coefficient of 2, there will be 4 hydrogens, and we have to deal with that. So we can add an H+, so that will be part of our reaction here. We'll have a coefficient of 4. So now we have balanced our equation, but we haven't balanced our charges. So here we have 4 plus, and then we have a minus, and then we have 0. So the charge here is going to be 3 plus in total for the entire reaction. Okay. So now to balance that out, we're going to have to add 3 electrons, and that'll remove our charge here. Let me just erase this. Okay. So now we have 2 reactions here. We have our oxidation reaction and our reduction reaction. However, we have a different amount of electrons, and we don't include electrons in our equation. So we're going to have to cancel out the electrons. The easiest way to do this is just by multiplying this by 3, because we'll end up with 3 electrons, and we can cancel that out at the end. So once we do that, we're going to end up with 3 AgS, 3 Ag plus, and 3 electrons. Now we can cancel out the electrons and add all this together. So in the end, we'll have 4 H plus, NO3 minus, 3 Ag, 3 Ag plus, NO, and 2 waters. So here is our final balanced redox reaction. Now let me just go and ask what the question is saying. So it says, what is the ratio of the coefficient of AgS to the coefficient of H2O? So here, pretty easily we can see the coefficient is 3, and the coefficient here is 2. So that's going to be a ratio of 3 to 2, which is answer option D. So, that's not a very fun question to do, but we have an easier one. How many sulfur atoms are in 3 grams of iron pyrite, FeS2, with a molar mass of 120? So, this is a very easy question, but I'm going to do it over here. Let me move this. Okay. So, we have 3 grams of iron pyrite, which is FeS2. And, yeah, we have, for every 1 mole, we have 120 grams of iron pyrite. Like that. So that's going to end up giving us around 0.025 moles of FeS2. And now we're going to have to find the sulfur atoms. So just like I said before with the other example, I think it was, I forgot, but I just mentioned some other example. We're going to have 0.25 moles of iron, but notice how there's a 2 on our sulfur. So that means that whatever amount of moles we're going to have here, which is 0.025, we're going to have to multiply that by 2, because we'll have 2 moles of sulfur as the reaction. So we're going to have 2 times 0.025, and that's going to be equal to 0.05 moles of sulfur. So now we have to get to atoms, right? Oh, to get to atoms here. Why is it doing this? Okay. Yeah, we have to get to atoms. So we're just going to simply multiply this by 6.022 times 10 to the 23rd, Avogadro's number. And, usually you don't have to type out the 10 to the 23rd. What I do is just, I see that it's equal to around 3.01. I look at the answer option and I see that there's only one. So that's going to be C. Or you can just do it aloud. I don't really care. Okay. Let me move all this again. So, how many chlorine atoms are in 1 milliliter of CCl4, which has a molar mass of 153.8 and a density of 1.59 grams for every milliliter? Milliliter. That's a weird word. Anyways, yeah, so this is pretty easy. D is equal to M over V. We're in milliliters, so we don't even need to convert to liters. So our density is going to be 1.95 grams per milliliter. And that's, we have our mass here. And our volume is going to be 1.0 milliliters. So we're going to be left with 1.59 grams of CCl4. So same thing here, right? Or actually, let's just go to moles first. For every 1 mole, we have 153.8 grams. So that is 0.0103 moles of CCl4. And we have 4 chlorine atoms, so it's going to be 4 moles of chlorine atoms times 0.0103. Sorry for my bad handwriting. And that's going to be, I don't know, 0.0412. Now we're going to multiply that by Avogadro's constant, or number, my bad. And that's 0.2481, which is very close to answer option D. I'm not even going to do the 10 to the 23rd thing, just to cut some time. Okay, time to go to the next page. Don't worry, it's only 2 questions. Okay, so sodium bicarbonate decomposes at high temperatures according to the following equation. So 2 moles of sodium bicarbonate decomposes into carbonate, or I forgot, bicarbonate, sodium bicarbonate, carbon dioxide, and water. At a certain temperature, 50 grams of sodium carbonate is allowed to react in a 3-liter evacuated vessel. At equilibrium, the total pressure is 6.25 atm, with some of both solids still present. If 100 grams of sodium bicarbonate is allowed to react in the same vessel at the same temperature, what will the pressure be at equilibrium? So really, this is just relating relationships. So as we see, 50 grams of NaHCO3 is going to react in a 3-liter evacuated vessel, and the total pressure is going to be 6.25 atm. So instead, we're going to have 100 grams of NaHCO3. So we can see that the mass is going to be changing. So that's going to be part of our formula. And then it's allowed to react at the same vessel at the same temperature. What would the pressure be at equilibrium? So the pressure is also going to change, right? So if we're going to be looking at our equilibrium equation, we can see that there's going to be two gases. There's going to be CO2 and H2O. So K of P is going to be equal to H2O, but not the concentration of H2O, the pressure of H2O, times the pressure of CO2. So as we see here, solids are going to be not in the equilibrium formula because it's a solid and it doesn't go into the formula. So we see that even if we change the mass of NaHCO3, it's not going to do anything to the equilibrium constant. And the equilibrium constant is the thing that will be changed, because that's what we're trying to find. The pressure at equilibrium. That's what we're finding. And the only two things that affect it is the pressure of H2O and the pressure of CO2. So since those two things are the only things that affect the Kp, adding 100 grams of NaHCO3 is not going to change the total pressure. So it'll just stay at 6.25. Yeah, so there's no point of even doing any of this. So final question. First generation automobile airbags were inflated by the decomposition of sodium azide, which has a molar mass of 65.02. So 2 moles of sodium azide forms 2 moles of Na plus 3 moles of atmospheric nitrogen. What mass of sodium azide would be required to inflate a 16-liter airbag to a pressure of 1.2 atm at 17 degrees Celsius? So this is a pretty obvious application of PV is equal to nRT. But the catch here is that what are we finding here? We are not finding, well, we know we're going to find the moles, right? But the moles of what? We're going to be finding the moles of N2, right? Because this equation is going to give us the airbag, the gas, that's going to be inflated. So we're not finding the solids, we're finding the gas, the moles of gas inside of that. And then we have to use stoichiometry, dimensional analysis to get to sodium azide. So let's do that. We have 1.2 atm. Our volume is going to be 16 liters. Bad writing. And that's going to be equal to N times, okay. So we know that's going to be, what, R, right? What are we going to use for R? We need to use this unit, because we need to cancel out atm, liters, moles, and Kelvin, right? So, no, we have to keep moles at the end. So, this has to be our unit, I think. So, that's going to be 0.08206. Instead of trying to just somehow get that, just memorize this, because this will probably be used multiple times in your lifetime. 0.08206 is going to be our Rydberg's constant. So, there we go. And then finally we have to convert Celsius into Kelvin. 17 plus 273. So, once you do this, we're going to be at 19.2 atm per liter is equal to, I think that's 223.7974. And this is going to be K, right? So once you multiply this, kelvins are going to cancel. Liters per atm over moles. As you see, moles is both at the bottom, or here. So when we divide by 23.9474, we have N. ATM is going to cancel, liters is going to cancel, and we're going to be left with moles. And it looks complicated, it is, but just memorize this, and you won't have to do all that. 0.81 moles of atmospheric nitrogen is going to be what we're ending up with. So we need to get to 2NaN3, and I'm going to rewrite this equation so I don't have to go back. Okay, so now we have to do some simple stoichiometry to get to 2NaN3. 0.81 moles of N2. So for every 2 moles of NaN3 we have 3 moles of N2. And they give us the molar mass here, which is 65.02. So for every 1 mole, we have 65.02 grams. We have 65.02 because we need to get to grams. 65.02 grams of NaN3 for every 1 mole. Okay, and this will give us 1108, and well, it's gonna be grams. Okay, this doesn't really match any of our answer options, but this rounds up to 35, right? And there's a lot of decimals, so I probably did my sig fig wrong, but there's no point of doing sig figs right now, so A is going to be the answer. Alright then, see you next time.